Chapter Hydrogen from 11th ncert. So let's start the chapter. Hydrogen, the most abundant element in the universe and third most abundant on the surface of globe, is being visualized as the major future source of energy. So these are the objectives of this chapter. After studying this unit, you will be able to present informed opinions on the position of hydrogen in the periodic table, identify the modes of occurrence and preparation of dihydrogen on a small and commercial scale, describe isotopes of hydrogen, explain how different elements combine with hydrogen to form ionic, molecular, and non stoichiometric compounds. Describe how an understanding of its properties can lead to production of useful substances and new technologies. Understand the structure of water and use the knowledge for explaining physical and chemical properties. Explain how environmental water quality depends on a variety of dissolved substances, difference between hard and soft water, and learn about water softening. Acquire the knowledge about heavy water and its importance. Understand the structure of hydrogen peroxide, learn its preparatory methods and properties, leading to manufacture of useful chemicals and cleaning of environment. Understand and use certain terms, for example, electron deficient, electron precise, electron rich, hydrogen economy, and hydrogenation, etc. So, hydrogen has the simplest atomic structure among all the elements as around us in nature. In atomic form, it consists of only one proton and one electron. However, in elemental form, it exists as a diatomic molecule and is called dihydrogen. It forms more compound than any other element. Do you know the global concern related to the energy can be overcome to a great extent by the use of hydrogen as a source of energy? In fact, hydrogen is of great industrial importance as you will learn in this unit. So the first topic is position of hydrogen in the periodic table. Hydrogen is the first element in the periodic table. However, its placement in the periodic table has been a subject of discussion in the past. As you know by now, the elements in periodic table are arranged according to their electronic configurations. Hydrogen has electronic configuration of 1s1. On one hand, its electronic configuration is similar to outer electronic configuration of alkali metals, which belongs to the first group of periodic table. On the other hand, like halogens with ns2np5 configuration belonging to the 17th group of periodic table, it is short by one electron to the corresponding noble gas configuration helium. Hydrogen therefore has resemblance to alkali metals which lose one electron to form unipositive ions, as well as with halogens which gain one electron to form negative ions. Like alkali metals, hydrogen forms oxides, halides, and sulfides. However, unlike alkali metals, it has a very high ionization enthalpy and does not possess metallic characteristics under normal conditions. In fact, in terms of ionization enthalpy, hydrogen resembles more with halogens. Ionization energy of lithium is 520 kJ per mole, fluorine is 1680 kJ per mole, and that of hydrogen is 1312 kJ per mole. Like halogen, it forms a diatomic molecule, combines with elements to form hydrides and a large number of covalent compounds. However, in terms of reactivity, it is very low as compared to halogens. In spite of the fact that hydrogen to a certain extent resembles both with alkali metals and halogens, it differs from them as well. Now the pertinent question arises as where should it be placed in the periodic table. Loss of one electron from hydrogen atom results in nucleus of approximately 1.5 into 10 raised to power minus 3 picometer size. This is extremely small as compared to normal atomic and ionic size of 50 to 200 picometer. As a consequence, H positive does not exist freely and is always associated with other atoms or molecules. Thus, it is unique in behavior and is therefore best placed separately in the periodic table. Now dihydrogen S2 occurrence. Dihydrogen is the most abundant element in the universe. 70% of total mass of universe is dihydrogen and is the principal element in solar atmosphere. The giant planet Jupiter and Saturn consist mostly of hydrogen. However, due to its light nature, it It is much less abundant, 0.15% by mass in the Earth's atmosphere. Of course, in the combined form, it constitutes 15.4% of the Earth's crust and the oceans. In the combined form, besides in water, it occurs in plants and animal tissues, carbohydrates, proteins, hydrates, including hydrocarbons, and many other compounds. Now, the topic is isotopes of hydrogen. Hydrogen has three isotopes: protium, deuterium, and tritium. Can you guess how these isotopes differ from each other? These isotopes differ from each other in respect of the presence of neutrons. Ordinary hydrogen, protium, has no neutrons. Deuterium, also known as heavy hydrogen, has one, and tritium has two neutrons in the nucleus. In the year 1934, an American scientist, Harold C. Urey, got Nobel Prize for separating hydrogen isotope of mass number 2 by physical methods. The predominant form is protium. Terrestrial hydrogen contains 0.0156% of deuterium, mostly in the form of Hd. The tritium concentration is about 1 atom per 10 raised to power 18 atoms of protium. Of these isotopes, only tritium is radioactive and emits low energy beta negative particles. So these properties are given of the hydrogen, like relative abundance, relative atomic mass, melting point, boiling point, density, enthalpy of fusion, enthalpy of vaporization, enthalpy of bond dissociation, internuclear distance, ionization enthalpy, electron gain enthalpy, covalent radius, and ionic radius. Since the isotopes have the same electronic configuration, they have almost the same chemical properties. The only difference is in their rates of reactions, mainly due to their different enthalpy of bond dissociation. However, in physical properties, these isotopes differ considerably due to their large mass differences. So the next topic is preparation of dihydrogen. How it is prepared? There are a number of methods for preparing dihydrogen from the metals and metal hydrides. First is laboratory preparation of dihydrogen. It is usually prepared by the reaction of granulated zinc with dilute hydrochloric acid. It can also be prepared by reaction of zinc with aqueous alkali, as given below. So, commercial production of dihydrogen. The commonly used process are outlined below. Electrolysis of acidified water using platinum electrodes give hydrogen. High purity dihydrogen is obtained by electrolyzing warm aqueous barium hydroxide solution between nickel electrodes. It is obtained as a byproduct in the manufacture of sodium hydroxide and chlorine by the electrolysis of brine solution. During electrolysis, the reactions that takes place are at anode. Chlorine dissociates to Cl2 and gives 2 electrons at cathode. Water gains electrons to form hydrogen and hydroxyl ions. The overall reaction is this. So, reaction of steam on hydrocarbons or coke at high temperature in the presence of catalyst also yields hydrogen. So, reaction of hydrocarbons with water at different temperatures gives carbon monoxides. The mixture of carbon monoxide and S2 is called water gas, as a mixture of carbon monoxide and hydrogen is used for the synthesis of methanol and a number of hydrocarbons. It is also called synthesis gas or syngas. Nowadays, syngas is produced from sewage, sawdust, scrap wood, newspapers, etc. The process of producing syngas from coal is called coal gasification. So this is the process used to prepare water gas. The production of dihydrogen can be increased by reacting carbon monoxide of syngas mixtures with steam in the presence of iron chromate as catalyst. This is called water gas shift reaction. Carbon dioxide is removed by scrubbing the sodium arsenide solution. Presently, approximately 77% of the industrial dihydrogen is produced from petrochemicals, 18% from coal, 4% from electrolysis of aqueous solutions, and 1% from other sources. So the next topic is properties of dihydrogen. First is physical property. Dihydrogen is a colorless, odorless, tasteless combustible gas. It is lighter than air and insoluble in water. Its other physical properties along with those of deuterium are given in the table. Next are chemical properties. The chemical behavior of dihydrogen, and for that matter any molecule, is determined to a large extent by bond dissociation enthalpy. The H to H bond dissociation enthalpy is the highest for a single bond between two atoms of any element. What inferences would you draw from this fact? It is because of the factor that dissociation of dihydrogen into its atoms is only approx 0.081% around 2000 K, which increased to 95.5% at 5000 Kelvin. Also, it is relatively inert at room temperature due to the high HH bond enthalpy. Thus, the atomic hydrogen is produced at a high temperature is an electric arc or under ultraviolet radiations. Since its orbital is incomplete with 1s1 electronic configuration, it does combine with almost all the elements. It accomplishes reactions by loss of only one electron to give H positive, gain of one electron to form hydride ion, and sharing electrons to form a single covalent bond. The chemistry of dihydrogen can be illustrated in the following reactions. So first is reaction with halogens. It reacts with halogen X2 to give hydrogen halides. While the reactions with fluorines occurs even in the dark, with iodine it requires a catalyst. Reaction with dioxygen. It reacts with dioxygen to form water. The reaction is highly exothermic. Next is reaction with dinitrogen. With dinitrogen it forms ammonia. This is the method for the manufacture of ammonia by Haber process. Next is reaction with metals. With many metals, it combines at a high temperature to yield the corresponding hydrides. Reaction with metal ions and metal oxides. It reduces some metal ions in aqueous solution and oxides of metals, less active than iron, into corresponding metals. A reaction with organic compounds. It reacts with many organic compounds in the presence of catalysts to give useful hydrogenated products of commercial importance. For example, hydrogenation of vegetable oils using nickel as catalyst gives edible fats, and hydroformylation of olefins yields aldehydes which further undergo reduction to give alcohols. So the next topic is uses of dihydrogen. The largest single use of dihydrogen is in the synthesis of ammonia, which is used in the manufacture of nitric acid and nitrogenous fertilizers. Dihydrogen is used in the manufacture of vanaspati fat by the hydrogenation of polyunsaturated vegetable oils like soya bean, cotton seeds, etc. It is used in manufacture of bulk organic chemicals, particularly methanol. It is widely used for manufacture of metal hydrides. It is used for the preparation of hydrogen chloride, a highly useful chemical. In metallurgical processes, it is used to reduce heavy metal oxides to metals. Atomic hydrogen and oxyhydrogen torches find use for cutting and welding purpose. Atomic hydrogen atoms produced by dissociation of dihydrogen with the help of electric arc are allowed to recombine on the surface of welded to generate the temperature of 4000 Kelvin. It is used as a rocket fuel in space research. Dihydrogen is used in fuel cells for generating electrical energy. It has many advantages over the conventional fossil fuels and electric power. It does not produce any pollution and releases greater energy per unit mass of fuel in comparison to gasoline and other fuels. So next topic is hydrides. Dihydrogen under certain reaction conditions combine with almost all elements except noble gases to form binary compounds called hydrides. If E is the symbol of an element, then hydrogen can be expressed as EHX. The hydrides are classified into three categories. First is ionic or saline or salt-like hydrides. Second is covalent or molecular hydrides. Third is metallic or non-stoichiometric hydrides. Ionic or saline hydrides. These are stoichiometric compounds of dihydrogen formed with most of the S-block elements which are highly electropositive in character. However, significant covalent character is found in lighter metal hydrides such as lithium hydride, beryllium hydride, and magnesium hydride. In fact, beryllium hydride and magnesium hydride are polymeric in structure. The ionic hydrides are crystalline, non-volatile, and non-conducting in solid state. However, their melts conduct electricity and on electrolysis liberate dihydrogen gas at anode, which confirms the existence of hydride ions. Saline hydride react violently with water, producing dihydrogen gas. Lithium hydride is rather unreactive at moderate temperatures with oxygen or chlorine. It is therefore used in the synthesis of other useful hydrides. Next is covalent or molecular hydrides. Dihydrogen forms molecular compounds with most of the p block elements. Most familiar examples are methane, ammonia, water, and hydrogen fluoride. For covalence, hydrogen compounds of non-metals also have been considered as hydrides. Being covalent, they are volatile compounds. Molecular hydrides are further classified according to the relative number of electrons and bonds in their Lewis structure into electron deficient, electron precise, and electron rich hydrides. An electron deficient hydride, as the name suggests, has too few electrons for writing its conventional Lewis structure. Diborane is an example. In fact, all elements of group 13 will form electron deficient compounds. What do we expect from this behavior? They act as Lewis acid, in a sense, electron acceptors. Electron precise compounds have the required number of electrons to write their conventional Lewis structure. All elements of group 14 form such compounds like methane, which are tetrahedral in geometry. Electron rich hydrides have excess electrons which are present as lone pairs. Elements of group 15 to 17 form such compounds. Ammonia has one lone pair, hydrogen has two, and hydrogen fluoride has three lone pairs. What do we expect from the behavior of such compounds? They will behave as Lewis base, in a sense electron donors. The presence of lone pairs on highly electronegative atoms like nitrogen, oxygen, and fluorine in hydrides result in hydrogen bond formation between the molecules. This leads to association of molecules. So next is metallic or non-stoichiometric hydrides. These are formed by many D block and F block elements. However, the metals of group 7, 8, and 9 do not form hydrides. Even from group 6, only chromium forms chromium hydride. These hydrides conduct heat and electricity, though not as efficiently as their parent metals do. Unlike saline hydrides, they are almost always non-stoichiometric, being deficient in hydrogen. For example, these are D block hydrides. The law of constant composition does not hold good in such hydrides. Earlier, it was thought that in these hydrides, hydrogen occupies interstitials in the metal lattice, producing distortion without any change in its type. Consequently, they were termed as interstitial hydrides. However, recent studies have shown that except for hydrides for nickel, palladium, cerium, and actinium, other hydrides of this class have lattice different from that of parent metal. The property of absorption of hydrogen or transition metals is widely used in catalytic reduction hydrogenation reactions for preparation of large number of compounds. Some of the metals like palladium and platinum can accommodate a very large volume of hydrogen and therefore can be used as its storage media. This property has high potential for hydrogen storage and as a source of energy. Next topic is water. A major part of all living organisms is made up of water. Human body has about 65% and some plants have as much as 95%. It is a crucial compound for the survival of all life forms. It is solvent of great importance. The distribution of water over the earth's surface is not uniform. The estimated world water supply is given in the below table. Next is physical properties of water. It is a colorless and tasteless liquid. Its physical properties are given in the table along with the physical properties of heavy water. The unusual properties of water in the condensed phase, liquid and solid states are due to presence of extensive hydrogen bonding between water molecules. This leads to high freezing point, high boiling point, high heat of vaporization, and high heat of fusion in comparison to H2S and H2SE. In comparison to other liquids, water has a high specific heat, thermal conductivity, surface tension, dipole moment, and dielectric constant, etc. These properties allow water to play a key role in the biosphere. The high heat of vaporization and heat capacity are responsible for moderation of climate and body temperature of living beings. It is an excellent solvent for transportation of ions and molecules required for plant and animal metabolism. Due to hydrogen bonding with polar molecules, even covalent compounds like alcohol and carbohydrates dissolve in water. Next is structure of water. In the gas phase, water is a bent molecule with a bond angle of 10.5 degree and OH bond length of 95.7 picometer as shown below. It is a highly polar molecule. Its orbital overlap picture is shown. In the liquid phase, water molecules are associated together by hydrogen bonds. The crystalline form of water is ice. At atmospheric pressure, ice crystallizes in the hexagonal form, but at very low temperature, it condenses to cubic form. Density of ice is less than that of water. Therefore, an ice cube floats on water. In winter season, ice formed on the surface of a lake provides thermal insulation which ensures the survival of aquatic life. This fact is of great ecological significance. Structure of ice. Ice has a highly ordered three-dimensional hydrogen bonded structure as shown below. Examination of ice crystals with X-ray shows that each hydrogen atom is surrounded tetrahedrally by four other oxygen atoms at a distance of 276 picometer. Hydrogen bonding gives ice a rather open type of structure with wide holes. These holes can hold some other molecules of appropriate size interstitially. Next is chemical properties of water. Water reacts with a large number of substances. Some of the important reactions are given below. First is amphoteric nature. It has the ability to act as an acid as well as a base. In a sense, it behaves as an amphoteric substance. In the Bronsted sense, it acts as an acid with ammonia and a base with H2S. These are the reactions it shows with the base and acids. Redox reactions involving water. Water can be easily reduced to dihydrogen by highly electropositive metals. So these are the reactions occurred in this case. Hydrolysis reaction. Due to high dielectric constant, it has a very strong hydrating tendency. It dissolves many ionic compounds. However, certain covalent and some ionic compounds are hydrolyzed in water. Next is hydrates formation. From aqueous solutions, many salts can be crystallized as hydrated salts, such as association of water is of different types. First is coordinated water, interstitial water, and then hydrogen bonded water. Hard and soft water. Rainwater is almost pure, may contain some dissolved gases from the atmosphere, being a good solvent. When it flows on the surface of earth, it dissolves many salts. Presence of calcium and magnesium salts in the form of hydrogen carbonate, chloride, and sulfate in water makes water hard. Hard water does not give lather with soap. Water free from soluble salts of calcium and magnesium is called soft water. It gives lather with soap easily. Hard water forms scum or precipitate with the soap. Soap containing sodium stearate reacts with hard water to precipitate out calcium or magnesium stearate. It is therefore unsuitable for laundry. It is harmful for boilers as well. Because of the deposition of salts in the form of scale, this reduces the efficiency of boiler. The hardness of water is of two types. First is temporary hardness and second is permanent hardness. Temporary hardness. Temporary hardness is due to presence of magnesium and calcium hydrogen carbonates. It can be removed by first boiling. During boiling, the soluble magnesium hydrogen carbonate is converted into soluble magnesium hydroxide and calcium hydrogen carbonate is changed to insoluble calcium carbonate. It is because of high solubility product of magnesium hydroxide as compared to that of magnesium carbonate that magnesium hydroxide is precipitated. These precipitates can be removed by filtration. Filtrate thus obtained will be soft water. Second is Clark's method. In this method, calculated amount of lime is added to hard water. It precipitates out calcium carbonate and magnesium hydroxide, which can be filtered off. Next type of hardness is permanent hardness. It is due to the presence of soluble salts of magnesium and calcium in the form of chloride and sulfates in water. Permanent hardness is not removed by boiling. It can be removed by the following methods. First is treatment with washing soda, which is sodium carbonate. Washing soda reacts with sodium, soluble calcium and magnesium, chloride and sulfates in hard water to form insoluble carbonates. Second is Calgon's method. Sodium hexametaphosphate, commercially called Calgon, When added to hard water, the following reactions takes place. The complex anion keeps the magnesium 2 positive and calcium 2 positive ions in solution. Second is ion exchange method. Third is ion exchange method. This method is also called zeolite permutes process. Hydrated sodium aluminium silicate is zeolite or permute. For the sake of simplicity, sodium aluminium silicate can be written as sodium NaZ. When this is added in hard water, exchange reactions takes place. Permute or zeolite is said to be exhausted when all the sodium in it is used up. It is regenerated for further use by treating with an aqueous sodium chloride solution. Fourth is synthetic reactions method. Nowadays, hard water is softened by using synthetic cation exchangers. This method is more efficient than zeolite process. Cation exchange resins contain large organic molecules with SO3H group and are water insoluble. Ion exchange resins is changed to RNA by treating it with sodium chloride. The resins exchange Na positive ions with calcium 2 positive and magnesium 2 positive ions present in hard water to make the water soft. Here R is resin anion. The resin can be regenerated by adding aqueous sodium chloride solution. Pure demineralized deionized water free from all soluble mineral salts is obtained by passing water successively through a cation exchange in the H positive form and an anion exchange in the OH negative form resins. So in the cation exchange process, H positive exchanges for sodium positive, calcium 2 positive, magnesium 2 positive and other cations present in water. This process results in proton release and thus makes the water acidic. In the anion exchange process, OH negative exchange for anions like Cl negative, HCO3 negative, SO42 negative, etc. present in water. OH negative ions thus liberated neutralize the H positive ions set free in the cation exchange. The exhausted cation and anion exchange resin beds are regenerated by treatment with dilute acid and alkali solutions respectively. Next is hydrogen peroxide H2O2. Hydrogen peroxide is an important chemical used in pollution control treatment of domestic and industrial effluents. Preparation. It can be prepared by following methods. First is acidifying barium peroxide and removing excess water by evaporation under reduced pressure gives hydrogen peroxide. This is the reaction involved in the preparation of hydrogen peroxide. Peroxodisulfate obtained by electrolytic oxidation of acidified sulfate solutions at high current density on hydrolysis yields hydrogen peroxide. This is the reaction involved in the process. This method is now used for laboratory preparation of D2O2. Third is industrially it is prepared by auto-oxidation of 2 alkaline thyrikinols. This is the reaction involved. In the case 1% H2O2 is formed, it is extracted with water and concentrated to approx 30% by mass by distillation under reduced pressure. It can be further concentrated to approx 85% by careful distillation under low pressure. The remaining water can be frozen out to obtain pure hydrogen peroxide. Next is physical properties of hydrogen peroxide. In the pure state, hydrogen peroxide is an almost colorless, very pale blue liquid. Its important physical properties are listed in the table. H2O2 is miscible with water in all proportions and forms a hydrate H2O2.S2O. A 30% solution of hydrogen peroxide is marketed at 100 volume hydrogen peroxide. It means that 1 milliliter of 30% H2O2 solution will give 100 volt of oxygen at STP. Commercially, it is marketed as 10 volt, which means it contains 3% of hydrogen peroxide. Next is structure. Hydrogen peroxide has a non-planar structure. The molecular dimensions in the gas phase and solid phase are shown below. Next is chemical properties of this compound. It acts as oxidizing as well as reducing agent in both acidic and alkaline media. Simple reactions are described below. Oxidizing action in acidic medium, reducing action in acidic medium, oxidizing action in basic medium, reducing action in basic medium. Next is storage. H2O2 decomposes slowly on exposure to light. In the presence of metal surface or traces of alkali present in glass containers, the above reaction is catalyzed. It is therefore stored in wax-lined glass or plastic vessels in dark. Urea can be added as a stabilizer. It is kept away from dust because dust can induce explosive decomposition of the compound. Next is uses. Its wide-scale use has led to tremendous increase in industrial production of hydrogen peroxide. Some of the uses are listed below. In daily life, it is used as a hair bleach and as a mild disinfectant. As an antiseptic, it is sold in the market as perhydrol. It is used to manufacture chemicals like sodium perborate and percarbonate, which are used in high quality detergents. It is used in synthesis of hydroquinone, tartaric acid and certain food products and pharmaceutical etc. It is employed in the industries as a bleaching agent for textiles, paper pulp, leather, oil, fats, etc. Nowadays, it is also used in environmental chemistry, for example, in pollution control, treatment of domestic and industrial effluents, oxidation of cyankles, restoration of aerobic conditions to sewage waste, etc. Next is heavy water D2O. It is extensively used as a moderator in nuclear reactions and in exchange reactions for the study of reaction mechanism. It can be prepared by exhaustive electrolysis of water or as a byproduct in some fertilizer industries. Its physical properties are given in the table. It is used for preparation of other deuterium compounds, for example. Next is dihydrogen as a fuel. Dihydrogen releases large quantities of heat on combustion. The data on energy released by combustion of fuels like dihydrogen, methane, LPG, etc. are compared in terms of same amounts in mole, mass and volume are shown in the table. From this table, it is clear that on a mass for mass basis, dihydrogen can release more energy than petrol, about 3 times. Moreover, pollutants in combustion of dihydrogen will be less than petrol. The only pollutant will be the oxide of nitrogen, dinitrogen, due to the presence of dinitrogen as impurity with dihydrogen. This is of course can be minimized by injecting a small amount of water into the cylinder to lower the temperature so that the reaction between dinitrogen and dioxygen may not take place. However, the mass of containers in which dihydrogen will be kept must be taken into consideration. A cylinder of compressed dihydrogen weigh about 30 times as much as a tank of petrol containing the same amount of energy. Also, hydrogen gas is converted into liquid state by cooling to 20 Kelvin. This would require expensive insulated tanks of metal alloy like these are in use for storage of dihydrogen in small quantities. These limitations have prompted researchers to search for alternative techniques to use dihydrogen in an efficient way. In this view, hydrogen economy is an alternative. The basic principle of hydrogen economy is the transportation and storage of energy in the form of liquid or gaseous dihydrogen. Advantage of hydrogen economy is that energy is transmitted in the form of dihydrogen and not as electric power. It is for the first time in the history of India that a pilot project using dihydrogen as a fuel was launched in October 2005 for running automobiles. Initially, 5% dihydrogen has been mixed in CNG for use in four-wheeler vehicles. The percentage of dihydrogen would be gradually increased to reach the optimum level. Nowadays, it is also used in fuel cells for generation of electric power. It is expected that economically viable and safe source of dihydrogen will be identified in the years to come for its usage as a common source of energy. So this was all about the chapter.